Hey everyone, this is Thomas Kilkenny. I'm the lead technical artist for media entertainment at Epic Games, and I'm here at the Epic Games Los Angeles research and development stage to review stage operation for in-camera visual effects in Unreal Engine 427.
Within the context of some of the tools that Unreal Engine offers for in-camera VFX, we're going to be looking at Unreal Insights, which comes with Unreal Engine, and it's a very powerful tool for visualizing all the traces that Unreal has as it runs. It can be extremely useful for understanding things like when a frame is taking too long, or maybe startup is longer than expected. There's some behavior that you want to understand better. Insights really can help in that regard. So the first thing you need to be aware of is that there is documentation online on Insights. You can go to this webpage. It has great information, and there's a little link here to the Unreal Insights reference, which has more specific information about things like command line options that are normally used, and some of the known trace channels that you can include when you start Unreal. For demonstration purposes, we're going to be using the in-camera VFX template project. I have a switchboard configuration ready for it. Just to show you what it's going to do, we're going to start the editor. It's going to open up the default map, and it has an in-display configuration, which you can examine by double-clicking the asset. It just consists of a cluster of a single node, and it has 4 viewports, 1, 2, 3, 4, building a sort of 4K window. And also it has one in-camera VFX camera, making it a total of 5 viewports, 4 smaller ones, and then one big one for the in-camera. So first of all, Insights, it can be found under the engine folder. So inside the engine folder, there's going to be folder core binaries, and then in Windows, you'd go to Win64, and then in there, it's going to be Unreal Insights, which you can just double click to open. And you open it to do one of two things. One is to have a live session with Unreal, or to open an existing trace. So how do you tell Unreal to capture a trace or connect to this session server? We're going to launch the Unreal instance or the cluster, any given cluster node, with some command line arguments. So you can scroll down to the in-display settings area. There's a part that says extra command line arguments. This is just equivalent to putting these on the command line when you launch the instance. So there are 2 mutually exclusive ways of starting Insights. One is using tracehost, and you give it an IP address. This is what we're going to be using in this short tutorial. And the second way is if you don't want to stress the network and you just want it to save to a file, you use a trace file, and you give it a path to your trace. Utrace. The extension is utrace. So we're just gonna let's put trace host in this case. We're gonna give it the local host address because I have it running on the same computer. However, if your server is running somewhere else, then you would put the IP address accordingly. We're just gonna launch it like this for testing purposes and see what happens. You see there's already a trace that showed up. This is the in-display node running. You don't see the full window because I have a low resolution, so everything doesn't look super small. But here, if we go back here, you can have this auto start analysis for live trace sessions, so it'll just sort of open it up automatically when it starts getting it. And then we can stop, we can stop the node and then examine our trace. So this had no sort of extra command line arguments to tell Unreal Insights what to show in here. So by default, it'll show CPU traces, which gives you some information. So CPU traces are anywhere in code where somebody has, let's say this one that says and display, NVAPI D3 D1X present. This one is exactly this one. So you just give me the name of the trace, and you'll see that this is you saying, oh, this is gonna be in the CPU trace channel, and that's why it shows up in there. And then however long this scope of code takes, which is gonna be mostly inside this function, the presentation function, then that's what's gonna basically show up the start and end points each time that it runs. It's basically what shows up in here. Now we're gonna examine other arguments that you may use to get more information. And by the way, notice that we have sort of three main areas here. One is the game thread, which is basically calculating the status of the simulation, positions of cameras, joints, actors, etc. The render thread, which is basically issuing rendering commands for rendering your frames. And you have the RHI thread, which is basically issuing those commands to the GPU. And then we're also going to see a GPU trace up here once we enable that. So the next argument that I want to show you is, get this back down here, is basically you're going to tell it which trace channels you want Unreal to put in the session. So for example, trace, we're going to put CPU, which is the default. But if you remove it, if you're explicit about the argument and then you don't include it, then it's not going to be enabled. And because a lot of the channels rely on the CPU channel being enabled, then those might not even show up. So always include the CPU one. So now we're going to include, let's say, the GPU channel. I'm going to relaunch. Give it a second to run. I'm going to exit. I'm going to go back to Insights and then open this new trace that showed up in there. And now as you can see, we have a GPU trace over here, which is showing us in a CPU timeline how the GPU is being utilized by Unreal Engine. And the next argument that I want to show you is one called stat named events. Which basically makes it show you information about certain kinds of traces, stats, traces from Unreal Engine. The way you enable them is with command line called stat named events. And these are a little heavy, gives you a lot more information on the traces, which we'll see in a second. Because they are heavy, and if you want to sort of not have your trace files be huge all the time, then you can actually enable them at runtime. So we're going to do that right now. So we're just going to leave this as it was without the stat named events. We're going to launch our cluster. And we're going to let it run for a few frames. And we're going to start named events by sending the command from switchboard, so all the nodes would get it if we were running a cluster with more than one node. You can see stat named events enabled, basically capturing more information into the trace file, and then you can just turn it off, and we can exit, and we're going to look at the trace. So you can see this is before we enabled it, and then this is enabled, and now this is disabled. So you get all kinds of stats information in your trace. Let's see if we can maybe compare a few things. So you see here we get the draw sync command, renderview family, which you're missing here. It just starts over here. And then it has a lot more things that you can look at depending on what you're interested in debugging or understanding from your traces. In code, they are slightly different. It's when you see this sort of scope cycle counter. Before it was something like this, and this one requires, something else to be declared somewhere else. It looks something like this actually, with the stat group name and etc. So they're slightly different, and it's just basically another kind of trace, CPU traces that you can get in your trace file. The next trace channel that we're gonna go over is called frame. We're gonna add frame here and leave our start named events turned on. And frame is basically going to give you information about start and end of the frame, both in game thread and render thread. I'm gonna let it run for a few seconds, exit, and then look at the trace that was generated. So as you can see, this panel is populated with the frame durations. You can click on the different frames and it'll start selecting the frames in your tracks panel. And the color here just means that it was more than 30 frames per second. Like it took longer than that. As you can see, it took like more than 66 milliseconds. And you can see there's like a different color on the bottom and on the top. So if you click on the bottom one, that's going to highlight the render thread section. And if you click on the top part, it's going to select your game thread section. But it corresponds to the same game frame number 124. So you may be interested in that. You're looking at your frame durations and one of them looks longer and you want to discover why that is. And in this case, it seems that the game thread held up the render thread because it was busy loading an object. The next trace channel that we're going to look at is called log. So we're going to go back here and append log to the list. And just so that we have more logs to look at, I'm going to change the verbosity of, let's say, this one and this one. So basically telling Unreal, hey, any log with, let's say, any render sync log with verbosity of very verbose or less should show up in the log files and in the trace file. The log verbosities are these. It can be fatal, error, warning, display, log, verbose, and verbose. So, for example, there's a log here called render sync, and it's a warning, and it has some message. So if you say, hey, my verbosity for this sync when I run Unreal is warning or verbose or very verbose, it means that these are gonna show up. We had something more like error on the verbosity. Well, this one is not severe enough for it to show up. So that's what it would mean if we had that kind of verbosity when we launch Unreal. So we're going to go back here, close this and launch our cluster. Let it run a few frames, exit, and now pick it up, look at it. And now we have this one here very populated with lots of logs that you can search for keywords, so it's really easy to find things in there. And the nice thing is that when you click on the particular log, it'll basically give you a bookmark in the tracks timeline, so that you know when that happened with respect to the rest of the frames in the timeline. So this is just a very powerful tool for searching for particular events or logs that you may be looking for. Maybe you're looking for a timeout log or similar kinds of events that you're basically wanting to identify. A couple more things that may turn out to be useful when you're looking at your logs. I'm going to reopen this one. Is if you find that you want to reorganize things because you're interested in something that, let's say this render thread is like pretty far from that one. You have a few options. If you just press the letter C, it'll sort of give you a compact mode, so it gives you like a really, really high level, vertically compressed overview of what's going on. So you may be able to, let's say, more easily select a range by looking at multiple, tracks at the same time. And then pressing C will put it back to what it was. Or maybe you want to send this one to the top, so you can say, hey, dock to the top. And now you have, let's say, the render thread right next to the GPU thread. And you can sort of keep reorganizing them to your liking. Also, you have, other panels or, tabs that you may want to explore. They can be seen from here. And also the traces for any given channel are put in the thread that they belong to. And some certain things, sort of run in other threads that may be named. For example, there's a few named threads like, TCP message transport thread, or, the audio thread, for example. And some of them are sort of anonymous, but they're, grabbed from a pool of threads. So for example, this one has some DDC activity. Sometimes it may happen that maybe you're running your Unreal project and your DDC server is over the VPN and it's kind of slow, and you're wondering why your project is taking so long to start. And then you may, look at this and find some clues. In fact, there is a trace channel called load time, which will also give you some information relevant to loading times that you may be interested in as well. And that's it. Maybe one last thing to mention is that when you're running a multi-GPU system, you will see two tracks, one for each GPU, and they will be labeled accordingly. And for example, if you're, as is typical with our in-camera VFX tool and display, you may want to render your inner frustum in the second GPU and then the other ones in the first GPU. Then you'll see only the inner frustum render GPU times in, GPU 1 track, and then the rest it'll look kind of like this in the first GPU track. And that's it. Thank you very much.
427 introduced a powerful new stage tool called Level Snapshots that allows us to create a save point of the state of the entire environment at any given moment and restore it selectively at a point later on. In order to take a snapshot, we can use this Take Snapshot button, which will bring up a dialog window. By default, we have the save path that it's going to go to, and an auto-generated name based on this wildcard setup here. But in order to find it a little easier, we'll just write this down as example, and then take a level snapshot. The save time will depend on your computer-specific specifications as well as your disk read-write speed. Now that we have a snapshot taken, we can go ahead and start making changes to our environment, like moving the end display stage around. Make it a little bit extreme. As well as making select changes to the environment, like moving this walkway. We can then open the level snapshot editor from the drop-down here and select our previous snapshot. By default, this will then show all of the actors that have been modified since we made these changes. A few of these are a result of automatic changes made by blueprints, but the ones that we see down here are the actors that we had consciously changed. If we want to filter this down to only a specific type of actor, say we only want to restore the NDC, we can add a filter group, add a filter to that group. We have included this level snapshot filter by class with the sample project in the marketplace, which allows you to specify that you want to restore an actor specifically by its class. So we'll go down here, say and display root actor, or display cluster root actor. Which is the parent class of all of the end-display actors, and then refresh our results. This will now only restore actors that are matching the specification of these classes. If we want to also include the change that we made to that piece of walkway, we can add that filter again. Change that class to static mesh. And refresh our results. Now that we've generated the list of rules that we want to follow, we can click Restore Level Snapshot, and our rule will pop back to the point it was at the time of the take. Each of these filter groups can be built out as complex or simple as you want, with each row being an AND statement. Say we want to restore only actors that are of the class end-display root actor, and which are a certain distance from the stage. Or we can use these OR statements, which say that it can either match this set of filters or that set of filters, and both will be accepted. Once you've built out a complex set of rules, you can use this Load Save Filter button and save this as a preset. So we'll just save it right up at the top as an example here. Clear out the filters that we have, and then load back our previous preset to restore the same set of rules that we built it on the time. We suggest that you built out a set of rules ahead of time on the day, so that you have everything you need prepared to recall a take at any point later down the line. All right, after you have your end-display config set up, the first thing you're going to want to do before coming to stage is configure a reusable stage level. We use these levels to be able to instantly add our stage configuration to any given environment on the day, so we don't have to worry about reconstructing our end-display setup in each individual environment. So you've made one here already. We called it the LARD stage for the Los Angeles Research and Development stage. I've opened it already, and we have just a basic end-display setup. We have our end-display config file, which we've configured earlier. I've added 2 light cards that we'll use later when we go over these tools, a tracking origin to keep all of our mocapped actors underneath, and then 2 cameras that are going to represent our tracked A and B cameras for our actual on-stage cameras. Once you have a level set up like this, nice and simple, you'll go over to the environment that you're going to be using. In this case, we'll use Space Junkyard in the Origin sample project that's available on the marketplace. We will create a stage level for it. So we have the LAR&D stage, and we have a Space Junkyard _ LAR&D. So we'll open this one up. Navigate to the Levels browser by going to Windows, Levels, and then we'll simply add in our LAR&D stage, which you can see is already added here. An important thing to note is that this stage needs to be made into always loaded. So we'll go to Change Streaming Method, and from Blueprint, make sure it's always loaded. This ensures that when the level is launched on end-display, this level is loaded already, and we're able to begin moving right into the end-display process. All right, so once you have your stage level prepared and you've been able to get your end-display config onto the wall, the next step is to begin configuring our inner frustum cameras. So if you remember when we created the stage level, we added 2 Cine camera actors that represent our 2 real-world camera actors. So what we've done in our end-display config is included 2 ICVFX camera components, which represent the inner frustums on the ICVFX setup. So what we'll do is assign a Cine camera actor reference between the correct Cine camera actor and the correct ICVFX camera component to show that the camera A is controlling the inner camera A frustum, and camera B is controlling the inner camera B frustum. In order to configure tracking on the wall, we're going to be leveraging LiveLink. So what we've done is gone ahead and add our LiveLink sources. In this case, we're using an OptiTrack source for our capture system on stage, and we have 2 subjects representing our cameras. So to configure that camera correctly, we'll go to our camera A, to the Details panel, and we'll add a LiveLink component controller. We will assign the correct component to control as being our camera component on camera A, and Alexa Mini LFA as the source for that camera. So with your scene configured, with your cameras for LiveLink assigned properly to the ICVFX camera components, the last thing to do is take your LiveLink preset that you've created, save that as a preset on disk. For example, here we have our OptiTrack preset for LAR&D. And then you'll go to your project settings, search for LiveLink, and specify your default LiveLink preset. This is going to ensure that your end-display render nodes load up the correct LiveLink sources that you specified in the LiveLink panel right when they start up and can immediately begin capturing the tracking data. Finally, if you're looking to do multi-camera frustoms instead of single cam setup, all you have to do is have your second camera set up in a similar way with its own LiveLink component controller and its own LiveLink source. Specify that in its own ICVFX camera component and enable it, and you'll end up with 2 cameras or more, depending on how many of these you have set up. With our inner frustum set up, our next step is to ensure that the frustum on the wall is filling enough space for the camera to allow enough breathing room for an operator on stage. So even though the frustum is configured to fill the entire camera frustum, we may find that as we pan back and forth, we begin to catch the edge of the frustum on the wall just because of the amount of latency we get in the system. So the way that we can account for this is to actually artificially increase the size of the frustum on the wall. And in order to do that, we go to the ICVFX camera component that represents the camera we're working with. In this case, that's camera A. And you'll find this property called field of view multiplier. So 1.0 means that this is tailored to the film back that we specified and the focal length of the camera that we're using. But if we go ahead and make that over to 1.5, we'll find that the frustum gets larger. In this case, it's even bleeding onto the ceiling a bit. And we give enough breathing room so that when we pan back and forth, we don't find ourselves catching the edge of the frustum. In addition to controlling the scale of the inner frustums, we've given the opportunity to change the resolution of both your inner and outer frustums in order to squeeze out the maximum performance you can get in the day. Oftentimes you may find that with maximum resolution for all of your inner and outer frustums, you aren't quite hitting the frame rate that you're desiring. To remedy this, you're able to adjust the outer frustum resolutions so that you can squeeze as much into the inner frustum that's in camera without worrying so much about the resolution of what's outside. So if you go to our end-display config actor to its root component, you see that we have this viewport screen percentage multiplier. If we adjust this to say 0.5, we'll find that the effective resolution of all of the outer frustums is lowered down. If we go to 0.1, it'll go even lower. Or we can control it individually on each frustum. Let's not go to 10. So let's say we want to do just W1, the left side of our wall here, down to 0.1, so that we've lowered the resolution of the left side of our wall while maintaining the right side. This is also able to be done on the inner frustums by going to the respective camera component, looking for its inner frustum screen percentage, and making the adjustment there. In cases where you still want to benefit from the real-time lighting and reflections of the LED wall, but are looking to do a background replacement later on, we offer the ability to replace the entire inner frustum with a chroma key of your choice. We can do this by going to our end display actor, to our ICVFX component that represents the camera that we're looking to replace, finding the chroma key section, and then clicking this Enable Inner Frustum Chroma Key. This is going to replace the entire frustum with that chroma key color. This can be any color that we choose. By default, it's going to be green. We can switch that over to blue. As well, we're able to change the chroma key markers. So we can disable them entirely by toggling the Enable Chroma Key Markers off. You can also change the markers by changing this marker tile RGBA texture. By default, we have tracking marker A and tracking marker B. But you can import your own texture and supply it here in order to pick a tracking marker of your choice. Finally, we're able to change the color of the tracking markers by changing this marker color picker here. While screen space effects are not recommended for use in a scene that's going to be used in in-camera visual effects, given the fact that each viewport is rendering independently, scenes which are dependent on those screen space effects or would wish to benefit from them as much as they can take advantage of overscanning the outer frustums. So while all you're going to see on the wall is what's visible within the range that's specified in your config, we do offer the ability to go to overscan on the outer frustums. So we go to our end display actor, to our root component, and search for overscan. We'll find viewport overscan for each of the independent viewports. So let's go to our viewport W1, change that to enabled for percent values. We can use pixel values as well if we want, and change our overscan on the left to overscan for maybe 50% on the left side. This is going to allow for the rendering of an additional 50% on the left side of the viewport that we aren't actually able to see, so that we have more room to warm up screen space effects or other effects that will depend on pixels coming in from the portions of the screen that we can't see. In addition, we offer the opportunity to adapt the resolution of the viewport that you're overscanning. By having this set to true, the resolution will increase in order to compensate for the changes that you're making, such that you don't lose resolution by stretching it out to an overscanned viewport. If this is not of concern to you, you can switch this to false, and you'll get better performance out of your overscan. Over the course of a shoot day, you may find that you need to do additional color grading directly to the wall, in addition to whatever you're doing further down your color grading pipeline. In order to do this, we can go to our end-display actor, go to our root component, search for color, and you'll come across this color grading settings. This is a stack of post-process settings that can be applied to individual viewports, the entire cluster, or the ICVFX camera component. To start, we'll go with the entire cluster settings. You can see this is a set of tailored post-process settings specifically for color grading. So to make some change obvious, we'll go to gain and we'll increase the red channel. And we see that we've added red significantly to the entire cluster. We can do this with any set of settings that are exposed here, from the saturation or contrast gamma, temperature tint, exposure compensation, so far down the line. If you wanted to make changes specifically to a specific viewport, we can do that as well with these per viewport color grading settings. You see we have one already set for the ceiling to make it a little bit darker with the -4 in the exposure compensation. But if we wanted to add another one, we go here, add an element. You'll see that we now have another member of the array. And we'll say that we want to specify this one as belonging only to wall 1. So we'll go here, set that we're going to do VPW1, which is the left side of our wall. And they'll begin making settings there. So we'll go ahead, go to global, gain, and let's say increase the blue channel this time. So you can see we have a bit of purple on the wall. By default, these settings are additive. So we're adding the blue on top of the red that we've already added in the global settings. If you would like to exclude the entire cluster settings, we can switch this include entire cluster color grading to off. And we'll get the changes only that were made on this per node basis. But for now, we'll leave those on. And we can have the stack built up in that way. If you want to make changes to the inner frustum, you can see that the entire color grading settings has already made that change. But additional changes specifically to your inner frustum are done on the ICVFX camera component. So we'll click there, again, search for color, and we have the color grading settings for the inner frustum. So we'll go ahead and make a change. Go to gain, or in this case, let's do exposure compensation. Make something a little bit different. We can go ahead and switch this up to, say, 3, and brighten up our inner frustum. This is, again, additive. If you would like to exclude the entire cluster color grading from the inner frustum, you can again switch this off, and we'll have only the changes that we've made in this particular section. Now, the inner frustum cannot be adjusted on a per viewport basis, but it can be adjusted on a per node basis. So let's say we wanted to increase the exposure compensation, but only on the cases where the frustum is on the left side of our wall, which is our node 1. So we'll add a per node color grading settings, scroll down, and specify that we want these to apply only when the frustum is on node 1. Or in this case, actually, it's node 4, because we've made some switches. We'll go to exposure compensation, and let's say make it darker on that side. So you see that we're applying those settings only to what's on the left side of our wall, because that's where the division between these nodes is. Again, you can specify what sections of the stack you want to include. Do you want the all nodes color grading, which is the one that we specified up above? Yes or no? So that's that +3 to exposure compensation that we had before. Do you want the entire cluster color grading from our end display component on the top here? We switch that off. We'll see that the red changes we made earlier are gone. Or we can switch it off entirely and just go back to the settings that we had specified without this. In addition to the more familiar color grading settings that can be specified for the wall, we also have the ability to leverage OpenColor.io to do color space conversions tailored to your specific camera and wall setup. The product in the marketplace comes with this example OCIO config that leverages some LUTs that are available within the OCIO plugin in Unreal Engine, but we have a few that are specifically calibrated for our wall and camera combination. In order to leverage your OpenColor.io asset, we go to our end display actor in the scene, go to its root component, and we search up OCIO. That'll give you an OCIO section where we're able to specify the configuration source that we're going to be using. In this case, it's our NANT end display OpenColor.io configuration, and then the source and destination color space that we're looking to use. This is particularly calibrated for our Arri camera that we're using on our walls here. If, however, you wanted to go ahead and make some different adjustments based on the viewports that you're using, say you wanted a different config specifically for the ceiling, you can add an element here, expand and set up your settings. So again, we'll go to and display color configuration, set up our source and destination color space, and we'll do something a little bit different just to make it a little more obvious. And then we'll say that you want this to specify only on our ceiling 1 and ceiling 2 viewports. Unlike the color grading settings, this is not additive. So we've just gone ahead and overridden the OpenColor.io asset that's being used for the ceiling versus the walls. The same thing can be done for the inner frustum by going to the ICVFX camera component that corresponds to your camera. In this case, we're doing the main camera A. Again, you can see we already have this configured specifically for our use cases, but we can go ahead and add a per node override, specify our config, our source and destination color space. In this case, we'll use the airy one specifically for our camera, and then say that we want this to occur only on node 4, which is when the frustum is on the left side of our wall. In this case, we'll have a different OpenColor.io configuration set up for the inner frustum depending on which node it is, which means that if it does span across 2 nodes, you will see a different setup on each side of the frustum. In situations where you're looking to render out the view from the camera after the fact, or simply want a reference for the movement of the camera on the day, we're able to use Take Recorder to directly record the movement of the camera from LiveLink so that a shot can be reconstructed at a later point. To do this, we'll go to Window, Cinematics, Take Recorder to open the Take Recorder panel. By default, this is configured to the take number that was last used. In this case, we're on Scene 1, Take 27. We can add in the camera that we're looking to record, either by going to plus source from actor and adding the camera, or by dragging in directly from the world outliner the camera that we're looking to record. There are a couple of options to take note of in Take Recorder. First, there's a couple of different ways that you can record the camera, but the main two are either as possessable or a spawnable. A possessable will apply the animation back to the original actor in the scene that was recorded, whereas a spawnable will spawn another instance of the actor that will only exist for the life of the take and play back the animation. In most cases, we suggest that you use a spawnable for this type of recording, as it avoids having to ensure that LiveLink is disabled on the camera and avoids having to have this entire stage setup still in the level when an artist comes back to work on the scene at a later point. Notably, there's also the store at current timecode and record timecode options. Start at current timecode will use the timecode that we have provided here and place the animation at that point in sequencer. Record timecode will then take that same timecode value and place it as a track on the actor in sequencer. And we'll take a look at the results of that when we're done recording. So with that configured, we'll do a record. And we'll cut on that. To review back the camera you recorded, we can click this eyeball icon to review the last recording. And as you can see, our animation starts at the timecode point at which we began the recording. And the camera itself has a timecode take track here with the hours, minutes, seconds, frames, and subframes of the timecode at the time of recording. By default, you'll also notice that it recorded the end display actor as well as the tracking origin. This is because it records each actor in its parent space, as well as attachments to each of those parent actors to ensure that you can restore the scene to that exact point at a later time. And in order to finally look back at that camera, we can lock camera A to the viewport and play back the shot that we had. If you're looking to then render this take out, we can click the Render This Movie option to bring up Movie Render Queue and render it out just as you would any other sequence.